For the thermochemistry homework set, there are 6 types of calculation questions. One of the types focuses on taking a mass of a material from our equation and figuring out how much heat was given off. In order to do that, we need to use the molar mass of the compound in question, and then use any conversion factors here given in the given in the equation to convert our heat of formation. So we'll start with the 15.1 grams of pentane, C5H12. We're going to convert that to moles of pentane by dividing by 72.15 grams of C5H12 per 1 mole of C5H12. And then we're going to say we have 1 mole of C5H12 here, and that's equal to 3505.8 kilojoules of energy. So for 1 mole of C5H12, we have 3505.8 kilojoules. So this will end up giving us negative 734 kilojoules of heat released. Now what you want to do is put this in with a positive value, so that way you get the correct answer going through and doing that calculation. If we go down and look at the next question type, we'll use the equation that's given and determine the amount of our octane that's needed to give off a certain amount of heat. So we're actually going to start with heat and work back to mass. So we're going to run this backwards. Here we're starting at 282 kilojoules of heat. From our equation, 11018 kilojoules of heat is given off for every 2 moles of C8H18 that's consumed, and every 1 mole of C8H18 is going to have a molar mass of 114.224 grams. So we're converting from heat to moles, and then from moles to mass of C8H18 octane. When we calculate this out, this is 5.85 grams of C8H18. Exactly the opposite of the previous question up here. Now, for question type 4. The specific heat capacity of liquid water is 4.18 joules per gram degree Celsius, or Kelvin. How many joules of heat are needed to raise the temperature of 1.91 grams of water from 14.6 degrees Celsius to 74.9 degrees Celsius? Alright, so we need our equation for heat. Q equals M times C sub S, the specific heat, times the change in temperature, which is TF minus TI. Here, we know it's 1.91 grams of water times the specific heat, which is 4.18 grams per joules per grams degrees Celsius, times change in temperature. Our final temperature is 74.9 degrees Celsius, and our initial temperature is 14.6 degrees Celsius. Therefore, when we plug and chug this into our equation, we should get 4.81 joules of energy on the calculator. Okay. Now, as we look at question 5, this is very similar to the question we've seen above. It says a sample of mercury absorbs 35.9 kilojoules of heat, resulting in a temperature rise of 92.9 degrees Celsius. Determine the mass in kilograms of the mercury sample if the specific heat capacity of mercury is 0.140 joules per gram degree Celsius. Okay, so we have Q equals M times C sub S times delta T. We're solving for M. M is going to be Q divided by C sub S times delta T. So our specific heat here is 35.9 kilojoules. But note, the specific heat capacity is in joules, so we need to convert this kilojoules into joules. So I'm just going to cheat and multiply by 10 to the third joules and have that conversion out of the way. We'll divide then by the 0.140 joules per gram degree Celsius and multiply by the change in temperature, 92.9 degrees Celsius. Popping this into the calculator comes out to be 2,760 grams, and we need to convert that into kilograms for our answer. So there's 1 kilogram and 1,000 grams, so this comes out to be 2.76 kilograms. Okay, so again, this is just taking our Q equals MC sub S delta T equation and solving for something other than Q. For question type 6, we have a slightly different question here. We're asked to find the delta H of reaction for the reaction of 3 iron 3 oxides plus carbon monoxide goes to Fe3O4 plus, that would be iron 2 oxides and CO2. Actually, sorry, iron 4 oxide and CO2. Anyways, to solve this, delta H of reaction is equal to the sum of delta HF products minus the sum of delta HF reactants. So, we lay this out. We're going to have 2 times delta HF of Fe3O4 and delta HF of CO2. And subtract 3 times delta HF of Fe2O3 plus delta HF of carbon monoxide. Now, throw some numbers in. 2 times negative 1118 kilojoules plus negative 394 kilojoules minus 3 times negative 824 kilojoules plus negative 111 kilojoules. If we solve each section, negative 2630 kilojoules for products minus negative 2583 kilojoules for reactants means that I will end up having negative 47 kilojoules of energy by running this reaction. Now, question 7 is a Hess's Law question, and there's a lot of these. And with Hess's Law, we're given 2 or more simplified equations that allow us to solve for an equation that's given. We want to determine delta HF for the reaction. P4 plus 10 Cl2 goes to 4 PCl5. Well, the first thing we want to do is find the equation that has P4 in it and make sure it's on the left, which is here. Okay, this one, the second equation, already has P4 on the left, so we can use it as is. P4 solid plus 6 CO2 gas goes to 4 PCl5. 3 gas, delta H of reaction, delta H not of reaction equals negative 1207 kilojoules. Okay. What we're going to do now is get rid of the PCl3. PCl3 is in the other equation. In order to get rid of it, we need to multiply this equation by negative 1, but there's also 4 equivalents of PCl3, so we also need to multiply by 4. So we're going to multiply this equation here by negative 4. Multiply by the negative reverses the PCl3 side. So now the PCl3 gas and Cl2 gas will be on the left, and we'll get the PCl5 solid on the right. Because we're multiplying by 4, I put a coefficient of 4 in front of each one of these. Now, because I multiplied the equation by negative 4, I have to multiply the delta H reaction by negative 4. So now, delta H of reaction is equal to negative 628 kilojoules, because that's what negative 4 times 157 is. Now we can take and add these two together. If I add these two together, we notice that the 4 PCl3s cancel out. They're an intermediate. We can then add up the Cl2s and get 10. So we'll have P4 solid plus 10 Cl2 gas goes to 4 PCl5 solid. If we double check our equation up here, it's exactly what we want. Now, because we're adding here, we can add these two together. So delta H naught reaction is going to be equal to negative 1,835 kilojoules, okay, which is what you want to report this as. You do not need to convert this to 3 significant figures.